Alright guys, in chapter 16 we're going over acid-base equilibrium. We start out by looking over definitions of acids and bases. There are three major definitions of acids and bases. The first two that we're going to look at are the Arrhenius definition and the Bronsted-Lowry definition. The Arrhenius definition is what you learned in Chem 1. Acids have hydrogens in them, bases have hydroxides in them. So you put them in water, they're going to make a lot of hydrogen ions and hydroxide ions. The problem is that this definition is very limited. It does not include some other acids and bases. So we move to a more inclusive definition, the Bronsted-Lowry acid and bases. Bronsted-Lowry says acids are proton donors, bases are proton acceptors. Now, one really important thing to know when you look at this definition is hydrogen ions are in fact protons. Let's see why. Okay, over here we have our hydrogen atom. Has its proton, has its electron. The most common isotope of hydrogen does not have a neutron at all. So it's just a proton and electron, nothing else. Now, if you take that electron away to make a hydrogen hydrogen ion, then all you're left with is a proton. That's it. So what you've got here now is a hydrogen ion, but what you've also got is a proton. So a hydrogen ion is a proton, and a proton could also be called a hydrogen ion, though it generally is not. And so it's important that you realize that when we say proton donors and proton acceptors, we're really saying hydrogen ion donors and hydrogen ion acceptors. And that's the way you're going to be looking at it in most chemical equations. If we take a look at this equation over here, we have NH3, which is ammonia. It accepts this hydrogen here to make ammonium NH4 positive. Since the NH3 accepted this hydrogen, this proton, that means that it is a base. Now, in this model here, it would not normally be considered a base because normally we wouldn't say it produces hydroxide ions because it doesn't have a hydroxide in it. But with this model here, then we do call it a base because it is a proton acceptor. Now, one thing I'm going to show you is that NH3 does actually produce hydrogen ions, and hydroxide ions, and we'll see how it does that a little bit later. Alright, so next thing we're going to look at here is how we can show these types of reactions, these proton transfer reactions, in a way that makes sense to us. The best way to show this is by using the common dissociation reaction for hydrochloric acid. Now, the first thing I'm going to show you is I'm going to show you the normal way that we have been seeing the dissociation of hydrochloric acid when you dissolve it in water. Now, normally we don't include water as a part of the reaction. We just say HCl dissociates into hydrogen ions and chloride ions. But there is a second way to show this reaction. Now, if you dissolve hydrochloric acid in water, you know that gets really hot. This is showing an exothermic reaction, showing a chemical reaction between the hydrochloric acid and the water, and we can show that in a chemical equation. If we do, it's going to look like this. We've got hydrochloric acid plus water. Now, keep in mind, I'm showing the exact same thing in both these reactions. I'm showing hydrochloric acid dissolving in water. But this time, my product is going to be something that looks like this. Now, what this thing is right here, this is the hydronium ion. The hydronium ion formed whenever this hydrogen from the hydrochloric acid came over here and attached to the water molecule to make this thing right here, okay, our hydronium ion. So why do we have two different equations for the exact same reaction, hydrochloric acid dissolving in water? And which one's the best one to use? Well, they're both different ways of showing the exact same reaction. But this one down here, the one that has water in it, is probably going to be the most accurate. Hydrochloric acid does react with water, And when it does, all those little hydrogen ions that are present in the hydrochloric acid detach. And they don't just float around. What happens is they get attracted. They get attracted to the polar water molecules and they attach themselves to them. And when they do that, they form a hydronium ion. And then the chloride ions are still floating around in the water as well. And so this reaction here is the best representation of what's physically occurring within the water itself. So why don't we use that equation all the time? Because this one's a lot simpler, and it's a lot easier, and it breaks it down into its most important components. While this one here is a little more complicated, and really the water doesn't matter that much. Now here's the most important thing for you guys to get out of this. These two reactions, they're the exact same reaction, exactly the same. The reactants are the same and the products are the same, even though they don't look the same. You have to be able to write this reaction either way. And if there's a problem that's asking you something about hydronium, even though there's no hydronium shown in the equation, you have to know that this and this are the same thing, and that they can be used interchangeably with one another. And so if you have a problem asking you about hydronium, but you only see this, that's okay, because hydrogen ions are the same thing as hydronium ions when you have an aqueous solution. Okay, let's finish this up by looking at both types of reaction, acid reaction and base reactions in water. If I have an acid reaction in water, like this one right here, the acid is always going to donate a hydrogen ion to the water. Right? For example, if I take a look at hydrochloric acid here and water, this hydrogen from the hydrochloric acid is going to come off and attach to the water. And when it does that, it's going to form hydronium ions, chloride ions. So when it does this, that makes HCl your proton donor, H2O your proton acceptor, so that makes HCl your acid, that makes H2O your base. If we take a look at a basic reaction, like for NH3, when NH3 reacts with water, the water will give up one of its hydrogen ions to attach that lone pair right there on NH3. That's going to make ammonium and hydroxide. So the H2O gave up its hydrogen, its proton, to the NH3. So that makes NH3 your base because it accepted a proton. That makes H2O your acid because it donated a proton. Now something interesting is if you compare this reaction up here with this reaction down here, notice that here water acted like a base, but here water acted like an acid. There are several compounds that can do this, that can act like an acid sometimes and a base sometimes. These types of compounds are called amphiprotic. Water is probably the most well-known amphiprotic substance. So how do you know if water is going to act like an acid or if it's going to act like a base? It just depends on what you're mixing it with. If you mix water with an acid, it's going to act like a base. If you mix water with a base, it's going to act like an acid.